Hi students, welcome to Infinity Learn by Sri Chaitanya, and today we are doing a quick take on rolling motion. What it involves, what the velocities of the different points are, we'll find that all out. First up, before we move into rolling motion, we need to understand what it's actually made up of. First part is pure translational motion. Now in pure translational motion, even whether if you have a wheel or an object or anything, pure translation means it moves as a whole in one direction. There is no rotation about that central point. Okay, so all of the points have the same velocity. If this moves with the velocity, if this central point moves with the velocity v, even the top point moves with the velocity v, even the bottom points moves with the same velocity v. Nothing is changing over here, and in this case this system is said to be slipping because it's slipping on this surface. If you have a wheel and if you move it here, you don't call it rolling, you call it slipping. So in slipping, key point is that the velocity of each point is same and in the same direction. Okay, if you pick any other point, all of the points have the same velocity in that direction v. Now with regards to that, in this case the friction between body and surface has to be zero. Why is that important? Because if there is a frictional force, then it will start turning it. You will now be having a torque because it's at a perpendicular distance from the central point. It will start turning it. So for pure translational motion, pure slipping, the frictional force in a wheel has to be zero. If it's a block, it's a different story because there are many other forces come into it, but in a wheel, frictional force has to be zero for there to be no slipping. Next, the body possesses only translational kinetic energy because it's just a translational motion. It's given by half mv square. You can deal with it even in terms of just the center of mass and the velocity of the center of mass. You can just consider the total mass as a whole and put that as the value of m. Now this is pure translation. Next up we are going to look at pure rotational motion. Now in pure rotational motion, you have the fixed point over here. No point moves horizontally. There's no translational motion. They all move. Each point if you pick, that's moving tangential to its surface. Okay, so it's moving tangential over here. It has an angular velocity omega. In this case, the rotation, the axis of rotation of the body is fixed. In this case, it will only possess rotational kinetic energy. Now remember, rotational kinetic energy is just going to come from the translational kinetic energy of each of the particles over here. If you add them all up, you will see you'll get it by moment of inertia into the angular velocity square. So this is pure rotation. Earlier one was pure translation. Next up, we have the case of pure rolling, in which you have both the translation and the rotation happening at the same time, which means the body is spinning with that angular velocity omega, but it's also moving forward with the speed v. So this center of mass has that speed v, but in this case the key takeaway is that all the points can have different speed. For instance, this bottom point has to have zero speed. This bottom point has zero speed in pure rolling, because on one hand the translational motion tries to give it a velocity v in this direction, but by the rotational motion it has a velocity of omega r in the opposite direction. So they both effectively cancel out, because in pure rolling v is equal to omega r, so the net velocity of the bottom point is equal to 0. Okay, so there is no relative motion between the at the point of contact. For this to happen, net velocity at a point of contact v minus omega r has to be 0, hence v has to be omega r. In pure rolling, if you get the angular velocity, you can find what is the velocity with which it's moving forward. Now with regards to the energy, since there is both translational and rotational motion happening at the same time, the kinetic energy is the sum total of both of them. So Kn is Kt plus Kr. So half mv square plus half I omega square. The good thing in pure rolling is that omega can be written as v by r. Omega can be written as v by r, and I is just mk square, where k is your radius of gyration. K is your radius of gyration. So I replaced with mk square and omega replaced with v by r. Remember, only in pure rolling is v is equal to omega r. If there is slipping and rolling, then it will be a different story. So you have both of them, you get the net kinetic energy is half mv square 1 plus k squared by r square. For different systems, this radius of gyration would be different. Hence, the amount of kinetic energy given to rotational versus the amount given to translational would be different. The weightages would be different. Now if we compare all three together, then you can see the different velocities at the different points. First up, for the translation, as you can see, top velocity of top point, middle point here, it's same. Like I said, velocity remains the same. For the rotational, for the pure rotational case, again the speed is the same of all the end points, all the extreme points. The speed remains the same. So here is v, this point is also v, this point is v. A point to note is that if you look at any point inside it, its velocity is going to be less because its v is equal to omega r. Here r value would be reduced, so it would be less. That does not happen for this. For this, even if you take an interior point, it's also going to have the same speed v because there is no dependence on that radius. Now when you're moving into pure rolling, then the bottom point, like I said, here the velocity, the translation velocity tries to take it forward, rotational velocity tries to turn it backwards, so they cancel each other out, and here the net velocity is 0. But up top you see that the normal motion v tries to take it forward, and by omega r, even the omega r tries to move it in the same direction. Omega r is also in that direction, so the net effect is 2 times. Omega r is also equal to v, so the net speed of the top point becomes 2v. Over here, the normal translational one tries to take it in this direction, the rotational one tries to take it downwards. That is why the net resultance becomes root 2v. This is just root over of v square plus v square perpendicular vectors. Again, in this case also, any interior point's velocity is going to be different from the velocities over here. Again, you can use v equal to omega r, consider this as your focus axis point, omega into whatever is the distance. Then consider this as r, this is r1, r2, and use v is equal to omega r, and you'll get the velocities of the points over here. Okay, so that is our discussion of rolling motion. If you add slipping and rolling, then things would just ensure that you have that extra part because of translational motion. Anyway, that's it for this session. I'll catch you all in the next one.